Hi guys, in this video what we're going to do is we're going to look at the idea of one-sided limits and continuous functions. So in the last video we looked at the idea of a limit, and what you can see here is that if we look at this function here, so we've got y is equal to fx, we can see that as it's coming from the left hand side here, and you can see it's going towards the value of 3, but then there's sort of like a disjoint and it comes down here, and as it's coming from the right hand side, then we're going towards the value of 1. Now that means that you can see here that the limit from the left, which is we write x is heading towards the limit from the negative, i.e. from the left hand side, we can see that that's going towards 3. If we have a look from the right as it's going in this direction, you can see that again, you can see it's a plus here instead of a minus. You can see that this is now going towards 1. That means they're going towards a different limit from each side. So this one's going to 3, this is going to 1. So therefore the left hand limit is not equal to the right hand limit, and the limit as x heads towards a doesn't exist, because you can see it's going to two different ones here. Okay, so the existence of a limit exists if and only if the one-sided limit, i.e. from the left and to the right, exist, that's the first thing, and are equal. Now if we're asked to calculate the limit of fx, we only have to check the one-sided limit if we're asked to. We suspect that one-sided limits are different, or it's a piecewise defined function with different rules for x on each side of a. And I'll show what that is in the next slide. So this is what we call a piecewise function. You can see here that we've essentially split it into two. So when x is less than or equal to 1, we take this function, and when x is greater than 1, it becomes this function. Now I've actually just shown you the diagram what's happening here. So if x is less than or equal to 1, you can see we've got this sort of like idea of a quadratic, which is this. And then after that, you can see 5 minus x is just a linear, and that gives us the straight line. So our graph looks something like this. Now I've been asked to determine if the limit x heading towards 1 of f of x exists, and if it does, find the limit. Well, we can look at the diagram here. We can see that as x heads towards 1, we can see that the y value is equal to 4. Now, as it's coming from the left, you can see it should be hitting 4, and as it's coming from the right, it appears to be hitting 4 too. So if we can show that the limit from the left is equal to the limit from the right, then obviously this has a limit, and we should find it's 4, guys. Okay, so let's see if that's the case. So you can see from the left, we've got this bit here. So the limit from the left-hand side, we have the limit coming from the left. Remember that the minus tells us it's coming from the left. And what we have is x squared plus 3. Remember, for a limit to try, all we do is we stick in the value. So this is equal to 1 squared plus 3, which is equal to 4. So from the left, the limit is equal to 4. And we can see that here from this curve here, it's going to 4 at this particular point of 1. Okay, now we're going to do exactly the same from the right. So again, all we do is we put in the value. So what we now have is 5 minus 1, because the limit is 1, and that again is equal to 4. Now notice that we'd expect that as well from the graph that I've drawn, or it's on the right hand side here. Notice that the left hand side limit coming from the left is equal to 4. The right coming from the right is equal to 4. This means that the limit does exist, and the limit is 4. If the limit from the left, i.e. this one, was not equal to the limit to the right, then there would be no limit at all. Okay, in this slide we're going to look at continuity, and the definition of continuity is given here. So the function f of x maps onto f of x is continuous at x is equal to a if 1. F of a is defined, 2. The limit as x heads towards a of f of x exists, and 3. The limit of x tending to a of f of x is equal to f of a. If one of these things is not true, it's not continuous. Okay, it's very, very straightforward. All right, so we test this, we test this, we test this. If one of them doesn't work, it's not continuous. Okay, so let's have a look at an example here. It says the function f is defined by f of x maps onto 2x plus 3 over x minus 2. Explain why f is not continuous at x is equal to 2. I'm sure most of you will realise why it isn't continuous as x is equal to 2 here, but just by looking at the denominator here. But let's do the tests. So the first one is f of a is defined. So what we're doing here, x is equal to a. So that there is my a. So we're trying to work out if f of a is defined. Okay, so let's have a look. So that means we're going to put 2 through. So we're working out f of 2. And if we put f of 2 in, that's going to equal 2 by 2 plus 3 over 2 minus 2. And if we work that out, we're going to get equal to 7 over 0. And if we have a division by 0, that means that it's not defined at x is equal to 2. So this breaks this first definition. That is f of a, i.e. f of 2, is not defined, which means that it is not continuous. Okay, so that means it's not continuous at x is equal to 2, which also means that it's not a continuous function. Okay, so let's have a look at this example here. So you can see what we have is we have a piecewise function where when it's less than or equal to 3, it follows x squared minus 1. When it's greater than 3, it follows 2x plus 1. It's being graphed here on the right hand side. So before x is less than or equal to 3, it's this part here, which is the quadratic function. And greater than 3, it's this bit here, which you can see is a linear function. Now, in order to see if it's continuous at x is equal to 3, the first thing we need to do is we need to work out f of a, where in this, remember, we have to work out that x is equal to a, and that means at 3. So we need to find the correct one for 3. Well, it's this one here, and we just need to check that it works, okay, to check that it is defined. So let's put that through. So x squared minus 1. And what we're going to do, so we've got f of x there is equal to that. That's the one we're going to check. I'm going to check that at 3. So f of 3 is equal to 3 squared minus 1, which is equal to 8. Therefore, that there is fine. Remember on the last slide what we had a division by 0 when we checked the x was equal to a, which meant that it was not defined, and therefore we could just stop there. Right, okay. The next thing we need to do now is to check that the limit on the left is equal to the limit on the right. We can see from our diagram here that this isn't going to be the case, but we'll do it with the maths. So the first thing we need to do is check the limit from the left. So lim as x heads towards, and it's going to be 3 from the minus of f of x, which is x squared minus 1. Okay, that's coming from the left. We're going to check that. We already have the answer. We put 3 in there before. We did that here, and we get an answer of 8. So we know when we put that in, that's equal to 3 squared minus 1, which is equal to 8. So that there is the limit coming from the left. Now we're going to take the limit coming from the right. So lim as x heads towards 3 from the right. That's where the positive comes from. And what we have now is the 2x plus 1. Okay, let's put the numbers in. So we get 2 by 3 plus 1, which is equal to 7. Now, hopefully you can see, guys, that 8 is not equal to 7, and therefore it can't be continuous at x is equal to 3.